Now logs are another way of thinking about exponents. So we saw exponents on the previous slide. What's a logarithm? Well, if we write something like log base 2, I don't know, 32. This is like saying if we have base 2, what value of x gives us 2x equals 32. And so logarithms are related to exponentials, and it's a different way of thinking about them. And to solve this question, if we have log base 2 associated with 32, we get, well, what's the value of this x? It's got to be equal to 2 to the power of 5. And so the answer to this is going to be 5. Now I went ahead and put together this table off camera, and I want to show you the relationship between writing equations in the logarithmic form and the exponential form. So we could have, if our previous example here in the logarithmic form, we had log base 2, 32, and that was equal to 5. Or we could have written 2 to the power of 5 is equal to 32. And we could take other log bases. So we were interested in log 10, log base 10, and so we're interested in 10 as the base. And what's it going to take to get log base 10 1000? Well, that's going to be if we've got 10x 1000, clearly 10 to the 3 to the exponent 3 is equal to 1000, and my log base 10 to the 1000, that's going to be equal to 3. I could take another log base. I could take log base, say, 5, and I want to know log base 5 125. Right, what's that? What's the answer to that going to be? If you plug that into a computational device, into a computer website, probably not your calculator. Your calculator typically just has log base 10 and log base natural exponent, which we're going to talk about a little bit later. This would be like, wow, I've got 5x is equal to 125, and you should be able to see that x is going to be equal to 3. So again, we have log base 5 125. If I want to go 5 to the exponent of something so that it's equal to 125, it's going to be 3. Let's work through evaluating some log functions. I've got log base 6 36. How does 6 to what exponent is equal to 36? Well, that's 6 to the power of 2. Right? That's what's going to, and so this thing is going to be equal to 2. Let's look at the next one, log 1 over 1000. So notice that there is no base here. If we just see log, that means we're evaluating log 10. Now, it can be a little bit confusing. Sometimes economists, we use something called the natural logarithm so much. Sometimes we just write log, and you're supposed to know that it's a natural logarithm. We'll talk about the natural logarithm in the next part, in the next series of videos. But for now, whenever you see log with no base, I want you to think log 10. So it's log 10. So here we actually have log base 10, 1 over 1000. And so 10 to the power of what is going to give us 1 over 1,000? Well, it's going to be 10 to the negative 3. That's equal to 1 over 1,000. It's equal to 1 over 10 cubed. And so this thing is going to be equal to negative 3. Right? And lastly, we have log base 4, 1. And what's that going to be equal to? Well, we have 4 to the power of something equal to 1. What's that going to be? Well, that's going to be 4 to the power of 0. Right? So x must be equal to 0. And log base 4, 1 is just equal to 0. Here's a quick one for you to try on your own. See if you can find the answer to this one. Press pause till you got the answer, then press play, and we'll solve it together. Well, we've got base 4, and 4 to the power of what is equal to 1 over 4? Well, that's x equal to negative 1. So this thing is going to be equal to negative 1. So here we are on ALEK. Let's see if our answer is correct. I'm going to put in negative 1, and I'll click the check button, and we properly evaluated this logarithm. Take a look at the first problem. Now, if you think about it, you can probably figure out what x is supposed to be. But let me show you a better method of solving it. Let's say we want to take 2 to the power of both sides of this expression. So I have 2 to the power of log base 2x is equal to 2 to the power of 5. So I can do that. I'm doing the same to both sides of the expression, but you can kind of think of it as I'm sort of coming underneath, almost coming from underneath and turning the equation into exponents. Now this left-hand side, whenever I have 2 log base 2x, this thing is just going to be equal to x. In fact, this is a general rule. If I have a log to the power of log base a and some value here, whatever that value is, these two operators are going to cancel each other out. And so if you go back to this question that we're working on, we end up with x is equal to 2 to the power of 5, and x is equal to 32, which you might have already known that was going to be the answer. But now you found an algebraic way. There's an algebraic rule that's going to let you solve for x without just kind of looking at it and factoring and knowing your multiplication table. Let's look at the second problem. We've got 4 to the power of x is equal to 64. Maybe you already know what x is going to be, but is there an algebraic way that we can solve for x? Yes, there is. Let's take log base 4 to the exponent of 4 to the exponent of x, and that's going to be equal to log base 4 64, and these parts here, that's this rule I showed you over there. They're going to cancel each other out, so we're just going to have x is equal to log base 4 64. And 4 to what power is going to be equal to 64? That's going to give us 3. Lastly, let's look at this problem right here. We've got log x is equal to 2.5. It's a little harder to know what x is just looking at this setup, but we can use the rule that I showed you, and we can take 10 to the power of log base 10x is equal to 10 to the power of 2.5. We're just left with x is equal to 10 to the power of 2.5. And then if we used a calculator, we can see that x is going to be approximately equal to 316.23.